VSEPR, VSEPR. Although that doesn't spell VSEPR. That spells VSEPR. But we say VSEPR because that's easier. But it stands for, right, there you go, valence shell electron pair repulsion theory. And it's a way for us to take what we've learned from the Lewis structures and then use that model to then make very, very strong predictions about what the molecules will actually look like in three-dimensional space. This is methane, CH4. Now, we often will draw CH4 kind of like this as a cross. Don't put this in your notes because I'm going to write other stuff up here. It's easy to diagram our Lewis structures like this. If we did the Lewis structure for methane, and I think maybe we even did this, I don't remember. I drew it like this as a cross, okay? But in nature, it doesn't exist as a cross. It exists as this shape, which is called a tetrahedron, okay? And we get a tetrahedron because what do we have? What do these bonds represent? What's really in this bond? This stick here. Electrons. In fact, 2 electrons that are shared between the atoms on either side of it, the balls, okay? What's the charge of an electron? Negative. So we've got negative electrons here, negative electrons here, negative electrons here, and negative electrons here, okay? Negative charges repel each other. So they can't go far away from each other though, because they're stuck. They're stuck to this central carbon. So they're forced to be together, yet they want to be as far away from each other as possible. So when that happens, they will naturally arrange themselves into the shape of a tetrahedron. That's the shape that we predict based on the repulsive, it's very disgusting, based on the repulsive nature of electrons wanting to be far away from each other, yet they're still attached to the central atom in this molecule. And it's only the valence electrons that we're concerned about. Those are the only electrons that we modeled in the Lewis structures. And if you remember back in chapter 3, those are the only electrons that are involved in chemical reactions, okay? So by taking count of the valence shell electrons and then thinking about what shapes they make when they repulse each other, yet still have to stay attached to the center, that in a nutshell is everything you need to know about VSEPR. And then all you have to do is think about it. But I'm going to always try to come back to the thought process. So when we think about this repulsion and the shapes, we can think about it in 2 ways. We can think about the geometry that the electrons take on, and we can think about the geometry that results in the molecule that we're looking at. And the only difference between the electron pair geometry and the molecular geometry is if we have lone pairs. All right, so lone pairs are going to be the difference between these two. Okay, but the electron pair geometry, this is going to be the relative position of all of the electron pairs. And remember that your electron pairs, they can either be a bonding pair or a non-bonding pair. And we're counting all of them. So bonding pair or a non-bonding pair. The bonding pair, of course, we call this a covalent bond. And the non-bonding pair, we call this a lone pair. Okay, remember those terms are interchangeable. I like to think of them as packets of electric charge or packets of negative charge. And I'll be using that term a lot because I think it's very useful to help you imagine in your mind how these things are taking shape. So think of this as packets of negative charge. Okay, and of course, it's going to be the relative position that they arrange themselves in naturally around the central atom. So this is going to be the relative Oh, I already wrote that, relative position. There you go. Okay, let's move on then to the molecular geometry. How is that different? Well, if you have lone pairs, the electrons will distribute themselves, but how will the atoms that are bonded actually be organized? That's what we're looking at here. The molecular geometry, this is going to be based on the bonding or the bonded atoms only. But the lone pairs will influence the position that those bonded atoms will take up. Because the lone pairs, they still have a repulsive force. There's just nothing attached to them for you to see. There's no atom there for you to see the shape. For example, this is ammonia. Now, this is in the shape of a little pyramid, okay? Because if we were to draw the Lewis structure, NH3, how many electrons for nitrogen? 5, plus 3 is 8, right? So we got nitrogen in the center, spokes on a wheel. The hydrogens are already satisfied because they can only have 2 electrons. 2, 4, 6. So we have a lone pair on the nitrogen. Now, if you think about the electron pair geometry, the electron pair is looking at the shared pairs and the lone pairs. How many packets of negative charge do you see surrounding? There's 1 shared pair, 2, 3, and then there's a 4th, the lone pair. There's 4 packets of negative charge that are all associated with the central atom, with the nitrogen. If we only had the electrons for VSEPR, thinking VSEPR, okay? If the only electrons associated with the nitrogen come from these bonds, then these will naturally arrange themselves in a plane. So it's naturally, by repulsion, the fact that they're still stuck to the center, it's going to arrange themselves with 3 equal bond angles like this. And they'll all be in a plane. Now that's if there's no lone pair. Like if this were boron trihydride instead of nitrogen trihydride, right? Boron trihydride, you can draw it out for yourself. That won't have any lone pairs on the center. So it would be flat. It would be something that we call trigonal planar. And you can actually see that written on the slide right here. Trigonal plane. Number 2, exhibit 2. Right, but that's not what ammonia is. Ammonia, we did the Lewis structure. From the right Lewis structure, we can then use what we're going to learn in VSEPR to figure out what the actual shape is going to be. There is a lone pair also associated with that nitrogen. Imagine that that lone pair is sitting up here on the top. You already deduced from looking at methane that if we had 4 packets, they arrange themselves in a tetrahedron, okay? So we still have those same 4 packets, except now one of them is in a lone pair that you can't see because there's no atom attached to it. That lone pair is only associated with the nitrogen in the center, but there's no bond, okay? But that still has a repulsive force on the other 3 bonded atoms. So it's going to push them out of what normally would have been a plane and push them down into a pyramid. So this has a different geometry to it. It's what we call a trigonal pyramid, which I don't have on this slide here, but I'll talk about that one later. Okay? That's the kind of thought process that goes into thinking about VSEPR period. You start with the correct Lewis structure. If you start with the wrong Lewis structure, you're going to make the wrong predictions using VSEPR. But if you start with the right one, we would find that this molecule in nature would form the geometry of what we call a trigonal pyramid. All right, so we're going to get there. Now let me step back a little bit and talk about these packets, all right? A little bit more. We're going to use something new called the steric number to count our packets of negative charge. And SN, I'm going to use that as the abbreviation for steric number. So think of these as your packets. And remember that they can come from lone pairs and they can come from the shared pairs. But now I want to modify that definition just a little bit. The steric number is going to be equal to the number of lone pairs. Now, not the number of electrons in the lone pairs. Now we're just looking at the packets. So the pairs are the packets, okay? The lone pairs. And instead of looking at the bonding pairs, we're going to look at the number of atoms bonded. Because as you'll see, we're going to consider both a single bond, a double bond, or a triple bond. We're going to still count that as one packet. Okay, so this is going to include single bonds, double bonds, triple bonds. These are all, it's a collection, all right? So when we have a double bond, for example, yes, there's 4 electrons there, okay? So they're gonna have more repulsion than 2 electrons, but they're still confined to the same package. That package is, those electrons are confined to that area between the 2 atoms that are sharing those 4 electrons, okay? So that's why we're calling a double bond, it's still one packet. If it's a triple bond, you've got 6 electrons in there, but those 6 electrons are all confined to that one package of negative charge, okay? So we're gonna count those packages. Maybe I should use package instead of packets of negative charge. And then we're going to apply our thought process about what VSEPR tells us. So let's go over some basic geometries here. And I'm going to also use these balloons to mimic, to model what we're drawing up here with the geometries. And these are going to be the electronic geometries now. So if the steric number is 2, that means you only have 2 packets of negative charge to think about. They can come from lone pairs, they can come from single bonds, double bonds, or triple bonds. It doesn't matter. But if you only have 2 packages of negative charge, those are the packages that want to get as far away from each other as possible, a linear arrangement. And the balloons, if you think about static electricity, static charge that surrounds the balloons, if you hooked up 2 balloons like this, they will orient in a linear fashion. Okay? So we've got linear. I already explained to you trigonal planar, and I already explained to you tetrahedral. Those are the natural shapes that these packages of negative charge will take on when they are all bound to a central atom. Now it gets a little bit more complicated when we start having more than 4 things bonded to the center. Now, if we had 4 things bonded to the center, like methane, we've got 2, 4, 6, 8 electrons. Carbon's in the center, carbon has a completed octet. Carbon can't expand its octet, so you can't have any more than 8 electrons associated with carbon. But you've seen some examples where the central atom can be hypervalent. And when the central atom is hypervalent, you can have larger geometries. One of them is called trigonal bipyramidal. This is where you have an SN of 5. And if you have an SN of 6, it's octahedral. And you'll notice that I've got the bond angles in here as well. Let me talk about bond angles in a second. Let me just highlight for now that these last 2, with an SN of 5 and an SN of 6, you only need to consider these if you're looking at a molecule that has the central atom is hypervalent. Now you do have to remember one thing, how many degrees are in a circle? Anyone remember that? 360, right? So you have 360 degrees in a circle. So if we split that up into a linear arrangement, then the bond angle will be 180 degrees. If we split it up 3 ways in trigonal planar, it's going to be 120 degrees, each one. And what's harder to see is when you split it up into 4 equal parts, but those equal parts are arranged in 3 dimensions, your bond angle is 109.5 degrees. Now, I don't expect you to remember every single bond angle that we discussed, but these basic ones, what I'm describing right now, this is what I call the base geometries. The base geometries is where we start with everything being equal. If we're talking about a molecule, they all have the same bonds in them. They're all bonded to hydrogen, or they're all bonded to fluorine. Everything's equal. This is what we start with. And if there's no lone pairs, then the electronic geometry will be the same as the molecular geometry. Simply put, these geometries that we're looking at here is just based on the steric number. But the steric number could be, look at the definition of steric number. It's the number of lone pairs plus the number of bonded atoms. Okay? If there's no lone pairs, then the steric number is just the number of bonded atoms. Whether they're single bonds or double bonds or triple bonds doesn't matter. It's the number of bonded atoms. Okay? So if there's no lone pairs, whatever we describe as that base geometry or the electron pair geometry, it will be exactly the same as the molecular geometry. But if we have some lone pairs in there, you will get different geometries. And let me just show you a few examples of that, okay? I'm going to jump ahead a little bit here and talk about this slide where we have an SN of 4. We're starting with tetrahedral. If you have an SN of 4, and these are things you can memorize these easily enough. I understand that there's some new complicated thought processes that we're talking about now, but just make yourself a small set of flashcards, all right? And just put it as SN is 2, it's linear. If SN is 3, it's trigonal planar. If SN is 4, it's tetrahedral, okay? Tetrahedral. Now, and it's tetrahedral if there's no lone pairs, then the molecular geometry is tetrahedral as well. So for example, here's our 2 models of today, methane and ammonia, okay? They both have a steric number of 4. Except for ammonia, one of those comes from a lone pair. So electronically, the electron pair geometries are the same. The electron pair geometries are tetrahedral for both of these, because we're just looking at the organization of the packages of negative charge. They all have 4 packages of negative charge. So, so methane here is going to be tetrahedral. Tetrahedral electronic geometry. And this will also be tetrahedral electronic geometry. And yes, I'm even going to take the time to write it down here for water, because look what we have with water. Look at the Lewis structure for water. It's got 1, 2, 3, 4 packages of negative charge that are all going to distribute themselves as far away as possible from the central atom, in this case, the atom being oxygen. So it's still going to be tetrahedral electron geometry. And that kind of goes with what I said on the earlier slide. If there's no lone pairs, like what we have in methane, then the electronic geometry is equal to the molecular geometry. Okay? There's no lone pairs. So it's also going to be tetrahedral molecular geometry. Now, I already went through the process with you on ammonia. There's a lone pair here, so it's going to be pushing these 3 bonds out of what the base geometry is. What's the base geometry if there's only three things attached? If there's only three packets? Trigonal, you have to look up here, trigonal planar. But this is no longer in a plane because it's not an SN of 3, it's an SN of 4. So this goes out of the plane and into what we call trigonal pyramid or trigonal pyramidal. Because if you looked at the geometry of the molecule, it's taking on the shape of a pyramid with 3 legs. It's not a tetrahedron. So that's what you would get. This is going to be the molecular geometry. When you have 3 atoms bonded and 1 non-bonding pair, that's going to be trigonal pyramidal. And then for this last one, it's still SN of 4. Everything on this slide is SN of 4. Okay. But now 2 of those packages are lone pairs. 2 lone pairs. That's what we have with water. There's 2 lone pairs. It started as a tetrahedron. Now we have 2 lone pairs and 2 bonding atoms. It's not linear. There's only 2 atoms bonded, but it's not linear. This is what we call bent or angular. And you'll see other examples where it may be bent, but maybe not bent because there's 2 lone pairs. You can explain everything that's not exhibiting hypervalency with these base geometries that go up to SN4, and then these additional names of shapes, right? Trigonal pyramid and bent or angular. Those all explain the molecules that we would take out. That we would find in nature that don't display hypervalency. Let's go through some of these more basic shapes in a little bit more detail now. And let's just start with the steric number of 2. We have 2 packages of negative charge. Those will be 180 degrees apart from each other. And one example that you've already seen lots of is carbon dioxide. Here's carbon dioxide down here at the bottom of this slide. We've got 2 oxygens that are bonded to the central carbon. If we were to actually do the Lewis structure of this, let me put the lone pairs on here. Although for VSEPR theory, we're only really concerned about the steric number of the central atom. This is what we're concerned about here, not the oxygens. The steric number on that carbon is only 2. Because even though there's double bonds, those double bonds are 2 shared pairs between the atoms. So they're still confined to a pretty small space between the axis of the carbon and the oxygens here. So let me just highlight these. We've got 1 packet here and 1 packet there. So the steric number is equal to 2. So the bond angle that we would measure on carbon dioxide is 180 degrees. And the base geometry for SN of 2, whether it's the electronic pair or whether it's molecular, okay, it's going to be linear. That's your base geometry. If we have an SN of 3, let's use an example for that. Let's use boron trihydride. This would be the final Lewis structure for boron trihydride. If we were to go through the individual steps, which I'm not going to do, we've done plenty of Lewis structures in chapter 4. But if you count up the valence electrons and you follow the rules of building a Lewis structure, you're going to end up with this. And this is one of those exceptions to the octet rule. Boron has an incomplete octet, but there's no way to give boron any more electrons here. And if we were to do formal charge, you'd find that the formal charges are all 0 on all of these atoms. So this is the correct and final Lewis structure for boron trihydride. The steric number here is 3. There's only 3 packages of negative charge. So the electron geometry, as well as the molecular geometry, is going to be trigonal planar. geometries are the same because there's no lone pairs here. Let's stick with Sn of 3, but now let's consider where we have, of those 3 packages of negative charge, 2 of them are with bonded atoms, and 1 of them is a non-bonding pair, a lone pair. And we've seen several examples of that. For example, when we did the Lewis structure for sulfur dioxide, SO2. And again, I'm not going to take you through that whole long story again, right? You can go back in your notes and review that. When we build the Lewis structure for sulfur dioxide, this was another example of an exception to the octet rule, where in its most stable form, the Lewis structure looked like this. And we had an expanded octet on the sulfur. Sulfur was showing hypervalency. And again, this gave us the most number of 0 formal charges. It gave us the most stable configuration of all those valence electrons. Now, if we try to look at the steric number, well, we've got 1 packet of negative charge here. It happens to be a double bond, but they're all confined to the same area between the 2 atoms involved in that double bond. We've got a second packet here, and then we've got a lone pair up here. So the Sn is still 3. The steric number is still 3, which means that electronically, these will still give us a trigonal planar geometry. Okay, so electronically, trigonal planar. But the molecular shape now, yeah, there's a question. So the question is, do we only pay attention to the lone pair on the central atom? And the answer is yes, because what we're coming up with now is the geometry of the molecule. So that's going to be the organization around the central atom. So for these exercises, we're only focused on the steric number of the central atom. We could identify the steric number on the oxygens, but it's not going to help us with the geometry of the overall molecule here. All right, so that's the electronic trigonal planar. But if we now look at the shape, the molecular shape, or the molecular geometry, what's it going to be? Any ideas? Yes. This would be bent, or sometimes we would call that angular, but I think your textbook only uses bent. And notice that I didn't draw the Lewis structure in a bent configuration. It's not the job of the Lewis structure to show what the molecular geometry is, although oftentimes we will purposefully draw it that way, depending on what it is you're trying to emphasize. Okay. But what I drew up on top is not incorrect. Here's another example. Ozone. We saw ozone before, right? This is another, it's very similar to sulfur dioxide. And here you can see the lone pair, it's still attached to the central, so it's part of the steric number. And so it's influencing the overall shape. If there's no lone pair here, what would the geometry be? It would be linear. Because then, if there's no lone pair, the steric number is back to 2. And 2 is linear. With a lone pair here, it's now putting it out of the linear because we still have repulsion occurring. Right? We still have repulsion occurring here. And then, of course, we went over this slide already. So I'm not going to go over this again. This is now showing you all of the other variations that you get when you have a steric number of 4. And all of the examples on this slide, all of these molecules have a steric number of 4. So let's focus a little bit on the bond angles. Notice back up here on the base geometries, we do have some bond angles listed here. And you don't have to memorize every single bond angle, but some of Some of them I do want you to know, right? The bond angles of the base geometries I want you to know. If it's linear, it's 180 degrees. If it's trigonal planar, they're going to be 120 degrees apart. And that's if all of the bonded atoms are equal. If it's tetrahedral, that might be one that's a little trickier to remember. It's 109.5 degrees in three-dimensional space for all four of those packets. And again, we'll talk about the other ones in a little bit here. But I want to have a little discussion with you just about the relative strength of the repulsion. Because the lone pair versus a shared pair, they're not as restricted to where those electrons can be found in 3D probabilistic space. If it's a shared pair, those shared electrons are more confined to the space between the atoms. But if it's a lone pair, they can expand their repulsive influence. So we can consider that. This is part of VSEPR as well. We can consider the relative repulsion. And as you might imagine then, lone pairs are going to have more of a repulsive force than shared pairs will in general. Okay, so lone pairs are typically exhibit more repulsion than shared pairs. And we can think of this in a couple of examples here. So if we were to say, look at two molecules where we have a lone pair versus bonding pairs, all right? So I think I didn't really need to write this because it's pretty much written here in the first bullet point. Repulsion between lone pairs and bonding pairs is greater than repulsion between two bonding pairs. So it's sort of saying the same thing. If I were to take two examples here, let's go back to boron trihydride with an SN of 3. Now, what's the bond angle between all three of those bonds? 120 degrees. They're all the same. Now, if we take a look at sulfur dioxide, and let's draw it in its shape, right? These both have an SN of 3 on the central atom. Okay, let's specify that, on central atom. That's really all we're focusing on in this discussion. But the bond angles are going to be a little different here, because here, one of the packets is a lone pair. It's got greater repulsion force than the shared pair does. So let's draw nice thick arrows here. Okay, now I don't want to put an actual number on what that bond angle is going to be here, but this bond angle here, it's going to be less than 120 degrees. And that's because the 120 degrees, that's happening when it's the repulsion all due to shared pairs. But now we've replaced one of the shared pairs with a lone pair. That lone pair is not as restricted in its probabilistic space. Let's write that in. Not as restricted to not area, let's do space, to space between two bonded atoms. So it can breathe more. And if it can breathe more, so to speak, right, those negative charges that are part of VSEPR have a greater sphere of influence. They can exert their repulsive force over a slightly greater area. So it's going to shrink the bond angle that we would measure between the two bonded atoms. All right, so I just want you to be thinking about this in a relativistic way here. All right, let's take a look at sulfur dioxide, but then another molecule that we did do the Lewis structure for this before. This is formaldehyde. What's the steric number on that carbon in formaldehyde? It's still 3. 1, 2, 3. And this is 3. 1, 2, 3. So again, the steric number is still 3 for both of these. Now, if we compare these two bond angles, let's just show it like this. Now, what we have is what's the stronger repulsive influence coming from the lone pair here on the sulfur dioxide versus the double bond on the formaldehyde. What this is telling you is that if you're just comparing that relative, because that lone pair, they can breathe more, right? They've got a greater zone of influence, but now we're comparing it to the repulsive strength of a double bond that is constricted in its probabilistic space between two bonded atoms. The lone pair is still going to be a little bit more repulsion. So let's show it this way. This will be smaller. In other words, we have more repulsion from the lone pair. In this case, relative to a double bond. And if we're not even looking at lone pairs, if we're just looking at single bonds versus double bonds, that one should make pretty straightforward sense. You're going to have more repulsion from a double bond than you will from a single bond. So if we were to compare boron trihydride here, now we're just comparing this bond angle and how much it's going to shrink if it's a single bond versus a double bond. Well, it's not going to shrink at all if it's a single bond. We already know that that's 120 degrees. But now you can probably figure out that because there's a double bond here, this is going to be less than 120 degrees. So this one is also going to be smaller. And earlier we talked about bent and who's more bent than someone else, right? You can actually take a look at two molecules that are both bent and assess what you think the relative differences in the bond angles are going to be of the bonded atoms using the same thing. And let's look at that compared to water. First of all, let's look at the steric number here. Now the steric number is going to be different. What's the steric number on sulfur dioxide? 3. What is it on water? It's 4. But what's the molecular shape of both of these? They're both bent. Okay. If we take a look at the bond angles, though, on sulfur dioxide, there's only one lone pair. On water, there's 2 lone pairs. So the 2 lone pairs are going to have a greater repulsive force than the 1 lone pair. So we would expect, once again, this one's going to be smaller. A smaller bond angle than this one, because there's greater repulsive force. This seems complicated. I'm just choosing these examples just to give you an idea of how to assess the relative strengths of the repulsive force coming from the lone versus the shared pairs. All right, so now let's get to those hypervalent geometries, and I'm just going to go through these in a methodical way to explain to you how we think about these and give you a few more names of the geometries that result when you have lone pairs in them. But I'm going to start with the base geometries and then work our way down by adding lone pairs to the molecule. And this slide might get a little complicated just because I want to put all of these SN5 examples all on one slide for you. Okay, so the steric number on the central atom is now going to be 5. And the base geometry for that, I think I've been using blue for the electron pair geometries. it will always be what we call trigonal bipyramidal. And this has two different bond angles associated with it. And I'm going to explain it to you. And if you're wondering why, the answer of why is this is how 5 packages of negative charge that are all bound to the center, how they will naturally arrange relative to each other, just based on natural repulsion. And if you were to, tie 5 balloons together, like what's shown in the earlier slide, because of the static electric charge on the outside of the balloons, if you tie them all to the center, they will also form this trigonal bipyramidal geometry. It's trigonal in the sense that you have an equatorial plane here, which is trigonal. So 1, 2, 3. And that trigonal plane, it's all 120 degrees bond angles, just like we had in trigonal planar. So this is what we call an equatorial trigonal plane. And from that equatorial trigonal plane, we have 2 pyramids. We've got a pyramid on the top, and we have a pyramid on the bottom. You can see that drawn here with these little, those should really be dashed lines, showing you where the name comes from. There's 2 trigonal pyramids. Now the bond angle, there's really only 5 bonds here. So let me draw those. The 3 that are in blue, that's in the trigonal plane. And then we have 2 that are axial to that plane. And when they're axial to the plane, that's at a right angle, 90 degrees to the plane. And again, these are just the geometries that explain, or just explain the observations. This is how they naturally will organize when you have 5 things, all with the same equal repulsive force. All right, so now you know where those 2 numbers, the 120 and the 90 degrees, come from. They all have the same base geometry for the electron pair geometry. Now the molecular geometry, let's consider what it's going to be. If we have 5 atoms, that means no lone pairs. So what's the molecular geometry going to be if all 5 of those pairs are bonded to atoms? Trigonal bipyramidal. Because if there's no lone pairs, that's another way of saying everything's bonded to an atom. That means there's no lone pairs. So with no lone pairs, it's going to be the same geometry as we have for the electronic geometry. So with 5 atoms, we're still going to be trigonal, trigonal bipyramidal. Okay, so here's an example of a molecule. Let's SF5. What would you call that? SF5. What's the name of that molecule? Say louder. Sulfur pentafluoride. Very good. Sulfur pentafluoride. I'm not going to draw the Lewis structure for it with all of the valence electrons. You can do that. But if we were to build a molecule of sulfur pentafluoride and then using VSEPR theory, those 5 fluorines are going to be arranged in the geometry that matches trigonal bipyramidal. All right. Now, let's consider what's going to happen when we have 4 atoms that are bonded and there's 1 non-bonding pair. What happens is we're going to use one non-bonding pair. This is our lone pair. Now remember that the lone pair, it has a greater sphere of repulsive influence, okay? And we're going to place this one lone pair somewhere in these 5 positions that it has the most space to breathe. And if you look at the bond angles, that's going to be one of the three equatorial positions. If you have one lone pair, it's always going to go in an equatorial position because that has the most space away from where all the other negative charges are. See, if we were to put that lone pair, for example, in one of these axial positions, put the lone pair down here, it's now 90 degrees away from these three in the equatorial plane. So that's closer than if we put the lone pair out here in one of the equatorial positions. Now, yes, it is 90 degrees from the axial, but it's also 120 degrees away from these guys. Okay, so it gives it more space overall. It's going to be most stable there in one of the equatorial positions, and that's just what you would find experimentally as well. There's more room for the lone pairs here. So if we stick just one lone pair, it's going to go in an equatorial position as shown here. Now, if we were to rotate that in this picture, all we're doing is rotating it so that we have the lone pair on the top. That means these two were equatorial and these two are axial. And this forms the shape of what we call a seesaw, or, seesaws, teeter-totters. Remember, as a kid, you would sit on one of those, and we can put a little person on here. Here, this will help you remember it. Well, that's a really bad stick person. Okay, this is the seesaw, and that's the name of this shape. That would be the molecular geometry when we have, oops, I put that under the wrong one, sorry. Seesaw goes under here. That's where the name comes from, because you turn it on its side and it has the shape of a seesaw. But in the middle, we're showing it with the lone pair, so you get an idea of what that looks like. Okay, if we just draw the overall molecular shape at the end on the right-hand side, that's showing it to you without the lone pair of electrons there. So an example that I'll give you for this molecule will be SF4. What's that called? This would be sulfur tetrafluoride, sorry. Right, and if we draw here, look, let's take a moment and actually do the Lewis structure for sulfur tetrafluoride now. Sulfur brings in 6. Each fluorine brings in 7 times 4 is 28. That's 34 electrons. We want sulfur in the middle, spokes on a wheel, connected by the 4 fluorines. Here they are. That puts 2, 4, 6, 8 in the shared pairs, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And we have 2 more to place. There's no other place for them to go, but sulfur can be hypervalent. This molecule does exist, SF4. So in our Lewis modeling system, we make sulfur hypervalent and put the lone pair on the sulfur. If you do your Lewis structure correctly, then you will have the right geometries that you can predict. 1, 2, 3, 4, 5. Steric number of 5 with 1 lone pair. That gives us a seesaw molecular shape. If we have 2 lone pairs, all right, so that means we have now 3 atoms that are bonded and 2 lone pairs. Well, that's going to be the example here in the middle. Once again, the second lone pair is still going to go in an equatorial position. There's more space for the lone pairs in the equatorial positions than they are in the axial positions. What that leaves in the end then is what we call a T-shaped molecule. That's the name of the molecular. I don't want you to think that sulfur tetrafluoride is T-shaped. Here, let's get rid of the we. We don't need that. I want to try to separate these. So T-shaped. Let me give you an example of a molecule that's T-shaped. Now we start to get kind of esoteric with our molecules. Normally when you see halogens in molecules, they typically will only form one bond, as you've been seeing so far. But there are some cases, some molecules, you will have some halogens that will form double bonds with themselves, not with themselves, but with other halogens. And this is one of those cases. This example will be ClF3. What would you call that? Say it louder. Chlorine trifluoride. They're all halogens, so each one brings in 7 valence electrons. There's 4 total, so that's going to give us 28 electrons to place. Spokes on a wheel. Chlorine is going to be in the center, symmetry, okay? It's also lower in electronegativity. Remember, fluorine is the most electronegative. All right, that places 6 of our 28 electrons in shared pairs. The rest all go as lone pairs. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We still have 4 left. We're going to put them all on the chlorine. Fluorine can't be hypervalent. All right. This molecule does exist. So the way we show it in the Lewis structure is we have to put the remaining lone pairs on the central atom. We got to make sure that the central atom can accept them all. Chlorine can be hypervalent. It's an N equals 3 or higher. So we're good. Chlorine's hypervalent. Notice all of these are examples of hypervalent, right? If you have an SN of 5 or an SN of 6, those are all hypervalent geometries, all right? The central atom is showing hypervalency. The steric number on that central atom, 1, 2, 3, 4, 5, SN of 5. 2 lone pairs, it forms a T shape. Right, there's one more shape to consider here when we now have 3 lone pairs and 2 bonded atoms. In this case, all will be in the equatorial plane. So all lone pairs. Let's just write all lone pairs. So if they're all in the equatorial plane, that leaves the 2 bonded atoms to be in the axial position. And if you look at the bond angles, axial position, those are 90 degrees each away from that equatorial plane. So what do you end up with here? What do you suppose this shape is called? It's linear. So here's another case where you can actually still get the same molecular geometry, but in this case, you've got a lot of lone pairs on the central atom, right? It's hypervalent, SN of 5, and you've got 3 lone pairs now. So here, let me give you an example of that. Now here's a case where we're not just only going to have, well, not only, I showed you one case where halogens will bond to each other. When we get to this level, we have some examples of noble gases that so far you've been taught that noble gases, they're already as stable as they can be at that stage. So there's no reason for them to undergo any kind of bonding to become even more stable. But there are some cases where noble gases will form covalent bonds when you get to the higher mass elements, like with krypton and xenon and so forth. And here's one example of that. Xenon difluoride. Xenon brings in 8 valence electrons. Each fluorine brings in 7, so that's 14. That gives us 22 electrons to place. And now our skeleton structure, we don't need spokes on a wheel. There's only 3 atoms here. So let's draw them in. Xenon, fluorine, and fluorine. That places 4 of our 22. Let's put the rest in. 6, 8, 10, 12, 14, 16, 18, 20, and 22. So xenon is being hypervalent. It can be. This material does exist. The steric number around that xenon is 5, 1, 2, 3, 4, 5, but this now has the 3 lone pairs. So those 2 fluorines will be in the axial position, and this is a linear molecule. So you've got a few more names to add to your stack of flashcards for your geometries when you are SN of 5. It's either going to be trigonal bipyramidal if there's no lone pairs, seesaw if there's 1 lone pair, T-shape, or linear. Let me at least get started on the SN of 6. There's not as many to describe for SN of 6. These are still hypervalent, but now we have 6 things attached to the center. That's going to form a shape that we call octahedral. That's the electron pair geometry. They're all going to be octahedral if your SN is 6. So again, you always start with the Lewis structure. So you got to go back to chapter 4 and remember all those steps and rules about building the right Lewis structure. And from that, you can then deduce what the steric number is. And from that, you can then deduce what the molecular shape will be. And then, as I said, on Wednesday, we're going to then start looking at new things that we can predict once we know what the molecular shape is going to be. All right, so octahedral is our base geometry. So with no lone pairs, the molecular geometry is going to be octahedral. And if we have 1 lone pair, well, now all positions are equal. These are all 90 degrees apart. So there's no one position that's more favorable than another as far as where that lone pair can go, right? So this lone pair can go in any position. But if you have a second lone pair, the second lone pair will always go on the opposite side as the first lone pair, because that gives the molecule the most stable arrangement of the 2 lone pairs in the context of the other 4 bonding pairs. So 2 lone pairs will always be in opposition. And again, it's all from the same reasoning of VSEPR theory, right? The repulsion that results from the electron pairs, in this case, from the lone pairs in this kind of configuration. All right, so if we look at the molecular shape that results from this, we now have another pyramid shape here. But in this case, the base isn't a trigonal base, it's a square base. And it's a pyramid. So what we call this is square pyramid. And in the case where we have 2 lone pairs, 2 non-bonding pairs, we end up with this shape. Because they will always be on opposite sides of the plane, that's going to then leave these 4 bonding pairs or 4 bonded atoms, they will be in a plane. So this one will actually be a cross or a plane. And that's, again, because we've got the same repulsion. I don't want to draw more red arrows here. You've got the same repulsive force from the lone pairs coming from opposite sides, right? It's going to leave the 4 bonded atoms that remain. They will be in a plane. So this could be drawn like a cross now, for example. So let me leave you with the 2 examples of molecules that would be shaped this way. This one, let's give you another funky one. Iodine pentafluoride. And this one will be xenon tetrafluoride. So let's just go through them really, really quick. I'm not going to spend a lot of time on this, but I'll show you very quickly all the steps that you would take, starting from, in this case, the molecular formula. And we know how to build that into a Lewis structure. There's 6 halogens here. And each halogen brings in 7 valence electrons. So 6 times 7 is 42. There's 42 electrons to place here. Our arrangement is going to be spokes on a wheel. Iodine is going to be in the center. 1, 2, 3, 4, 5 fluorines surrounding it. Those 5 covalent bonds use 10 of our 42 electrons. Let's place the rest. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. And then the other 2 will go on the central iodine, which was already hypervalent, by the way, when we hooked up 5 fluorines to it, right? But iodine can be hypervalent. It's coming from the period 3 or greater. So now we've checked all of our rules of building a Lewis structure. We know that this is the stablest Lewis structure. If you want to convince yourself and do formal charge, you'll find that the formal charge on all of these is 0. Each fluorine brings in 7 valence electrons, and it's surrounded by 1, 2, 3, 4, 5, 6, and then half of these, 7. And the iodine brings in 7 valence electrons, and it's surrounded by 1, 2, and half of all these, 3, 4, 5, 6, 7. So formal charges are 0 all around. This is your stablest structure, and we have iodine hypervalent in it. From that, then, we can then ask, all right, well, what's the steric number around that iodine? How many packages of negative charge are there? There's 1, 2, 3, 4, 5, 6. So that means I have an SN of 6. So I know, because I've been studying, that my base geometry for SN of 6 is octahedral. But now I've got 1 lone pair. So I got to remember, when my base geometry is octahedral with 1 lone pair, that gives me a square pyramid geometry. All right, and those are all the steps. Let's do it real quick for xenon tetrafluoride. Xenon brings in 8. Each fluorine brings in 7 times 4 is 28 plus 8. That's 36 electrons. Spokes on a wheel, xenon in the middle. 4 fluorines attached. The covalent bonds use up 8 of our 36 electrons. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 4 more to put, and I'm going to put those on the xenon because xenon can be hypervalent. So that's 34 and 36. Now here I put them both on the top, just to emphasize that the job of the Lewis structure is just to show the most stablest configuration of the lone pairs and the shared pairs. Those are the valence electrons. It doesn't have to show the shape. But let's go ahead and do that. I'm going to go ahead and put the lone pairs. I'm going to put 1 on the top and 1 on the bottom to mimic what's happening with VSEPR, because I know that with an SN of 6, by the way, here, I'm jumping ahead. Formal charge. The formal charge on all of these is still 0. 0s for the fluorines, just as before. The xenon comes in with 8 valence electrons, and it's surrounded by 1, 2, 3, 4, and then half of these, 5, 6, 7, 8. So once again, this is the stablest Lewis structure. Steric number 1, 2, 3, 4, 5, 6. So I know that I'm starting with octahedral, and now I've got 2 lone pairs. That gives me the square planar geometry. So this is called square planar. That's the geometry here. It's a plane, and the plane is now made up of 4 points. So all 4 points are on the same plane. So it's a square plane. Okay, so those are the steps that you should know how to go through then, starting from chapter 4 and building the Lewis structure, and then chapter 5 using VSEPR theory to interpret what that Lewis structure is telling you. And now we're going to see what can we do with those interpretations. Why do we care that we can tell what the geometry is? Okay.